Hi everybody, welcome back. So today we are going to we're going to continue talking about polar coordinates, and we're going to be talking about polar equations and polar graphs. And it's kind of nice because we'll be seeing that there are some familiar shapes that we can't really graph with x and y coordinates, but we can graph with polar coordinates. So we'll see that. This is going to be especially useful for those of you who are planning on going into calculus, particularly calculus 2 and 3. You'll definitely see this stuff again there. So you might want to save these notes for whenever. I know it might seem like a long time from now, but this is pretty. You'll learn this stuff again in calculus 2. So we already looked at how some polar equations can be graphed. Remember that if you have a polar coordinate, the polar coordinate of a point is given by r and theta, where r is the distance from the origin, and theta is the angle that this ray makes with the positive x-axis. Now, of course, theta and r are not necessarily unique, but this is one representation of this point using polar coordinates. And if r is always a constant, let's say some positive number a, then this is really just nothing but a circle centered at the origin, because we're just talking about all the points whose distance from the origin is equal to a. Another thing we saw was if we set theta equal to a constant and let r be anything we want, we get the point on this line that makes an angle of lambda with the positive x-axis, right? So the slope of this would be the tangent of lambda, but that's neither here nor there. Okay, or I guess maybe it is important, but we won't. We'll just move on. We also said that we saw that if we have an equation like this, r sine theta equals a constant, that looks kind of intimidating until you realize r sine theta is just y from our conversion equations. And so this is just the graph of y equals a, which is a horizontal line. So this always gives us a horizontal line. And r cosine theta equals a gives us a vertical line, because r cosine theta, remember, is x. So we get this vertical line, x equals a. All right, now I've added some stuff here because my camera crashed the first time I was doing this video. So let me just say, now we're looking at graphs of the form r equals 2a sine theta and r equals 2a cosine theta. These turn out to be circles, but these are circles that are not centered at the origin. Okay, so just let me show you. If you had r equals 2a sine theta, if you want to see why this works, we can first multiply both sides by r, and we'll get r squared equals 2ar sine theta. And then r squared, remember, is x squared plus y squared. And then we have 2a, and r sine theta is y. We can take the 2ay over here, and so this is 0. But now we're going to complete the square. So remember how we do that. If we take minus 2y, minus 2a, we divide by 2a minus 2a divided by 2 is minus a, and then we square it, we get a squared. So we'll add a squared to both sides. Okay, and then this factors as x minus a squared. This is x squared still, and this is equal to a squared. Okay, so this is, and I'm sorry, this should be a y. So this is a circle of radius a, centered at the point 0a. Okay, and that's exactly what we have right here. Okay, we can do the same thing here and see that we get a circle centered at a comma 0. If we do the same thing here with a minus here, we get a circle centered at 0 minus a, and here we get a circle centered at minus a 0. Okay, so all these are circles. Okay. Okay, now some more interesting graphs that we can get are these cardioids. These aren't cardioids, they're hearts, as some other people call them. These are hearts. Okay, that they look like looks like you have 4 different graphs. Depending on what the equation is, you have a heart. You know, it's on its side or upside down or something like that. Cardioids, we have so like this. If a is a positive constant, if the r equals a times the quantity 1 plus cosine of theta, this gives you something like this on its side. Now the reason for this is we get this is the easiest way, if you want to get a quick idea if you must plot points doing these graphs, you want to do this with plot the angles for the simple angles, 0, pi over 2, pi, and 3 pi over 2. Okay. So in this case, if we let theta equal 0, we get 1 plus 1, this cosine is 1, so you get 2a. And that's how you get this point. When pi over 2, cosine of 0, so you just get a. At pi, this is negative 1, so you get 0, you get here. And then at 3 pi over 2, you get, this is going to be 0 again, so you get a. So that's how you get these 4 points. Now that won't, normally that won't be enough, but it will in this case if you recognize that this is a cardioid. Okay. Then we have these other versions. We have we can have a times 1 plus sine theta, or 1 minus cosine theta, 1 minus sine theta. You get these hearts, and we get the usual looking heart when in this last situation. Okay, if you just plot some points, you see that this works out. So here's a heart. If you want to give your on Valentine's Day, if you want to give your Valentine something, you can hand them a card with this equation on it, and your Valentine will become your ex-Valentine very quickly, but at least you'll be showing off your math skills, I guess. Okay. Some other cases. So what happens if we have a constant plus another constant times either sine or cosine? Well, we get something of what we call a limacon without an inner loop, and this is really kind of a deformed thing where we kind of pop the pimple here, and we just have this elongated egg shaped here. And once again, you can find these 4 points just by plugging theta equals 0, pi over 2, pi, and 3 pi over 2 in here. So you can be aware of this. And then the interesting one is, so this is when A is bigger than B. If B is bigger than A, then we have something else. Okay, then we have these what we call limacons with an inner loop. Okay, and this is going to be where the graph actually passes through the origin many times. Okay, so you have that, and you can plot. Plug in a few points, like so when theta equals 0 here, you get a plus b. When theta equals pi over 2, you get a plus b times 0. When you have theta equals pi, you get a minus b. Well, a minus b when theta equals pi, well, pi would be in this direction, okay? So the opposite of a minus b would be b minus a, so that's why we're over here. Yeah, just think about that. Or don't think about it too hard, but you'll see that these all work. So these are limacons with an inner loop, so you want to see if b is bigger than a or a is bigger than b. And then we have these nice rose curves. And the one thing I'll just say about that is you got these nice curves where you have r is equal to a cosine of n theta and a, or r equals sine of n theta. The thing here is when the number of petals given is determined by what it's going to be n if n is odd, but if n is even, it's 2n for some reason. Okay, so when n is 2, we get 4 petals. When n is 3, we get 3 petals because 3 is odd right here. All right, so again, that's kind of nice. You'll be learning a lot more about this in Calculus 2, and for those of you who do this. Just take that. Some other nice graphs are spirals. Spirals, okay, and we'll just say the real simple equation is r equals theta. That's what where it's the more the angle rotates, the bigger r is. So this spiral actually goes on forever. It spirals out of control, I guess. It starts obviously when theta is 0, r is 0, and then this point would have to be pi over 2, and then this would be pi, and this would be 3 pi over 2, and this would be 2 pi, and so on. So we get, that's what we call our spiral of Archimedes, the famous Greek one of the famous Greek mathematicians. And then we get a slightly different spiral if we have r equals e to the theta divided by some lambda, some constant lambda. The thing here is, of course, this does not go through the origin because r e raised to any real number can never be 0. Okay, it's always strictly positive. So we have this open circle here, but it basically kind of looks like the same, except, of course, this would be, for example, here, this would be pi over 2 divided by lambda. Okay, so, or rather, the coordinate here would be e to the pi over 2 divided by lambda, so this would be like that. All right, so that's the logarithmic spiral for some reason. So keep in mind symmetry, how symmetry works with these polar graphs, or with polar coordinates. A reflection through the x-axis corresponds to just changing the sign of theta. And because, if this is theta, then this would be minus theta. And a reflection through the y-axis would be this. It would be replacing theta with pi minus theta. So if this is theta, from here to here is pi. So from here to here, that would be pi. This would be pi minus theta. Well, actually, this angle, I guess, would be pi minus theta. Okay, so this substitution corresponds to a reflection through the y-axis, and then if we wanted to just find the point that's symmetric through the origin, there are two ways we can do this. We can just replace r with minus r. That's probably the easiest way. Or you can add or subtract pi to theta. So, like I said, there are many polar coordinate representations. So, as we say, if to divide the symmetry, if theta is replaced with minus theta, and if that substitution doesn't change the equation after you simplify it, the graph has to be symmetric to the x-axis. If the substitution theta was replaced with pi minus theta, if that doesn't change it, then the graph is symmetric to the y-axis. And if r is replaced with minus r, or theta is replaced with theta plus or minus pi, if that doesn't change the equation, the graph is symmetric to the origin. Okay. So now a lot of these graphs here, some of these there's not much symmetry here, but hopefully you can see like this, the difference from here to here, this graph is really a reflection through the y-axis. And what's going on here is we've replaced theta with pi minus theta, because this is we've replaced cosine of theta with minus cosine theta. Well, that's the effect of replacing theta with pi minus theta. Okay, And then this of course would be this reflected through the x-axis gives us this, and this corresponds to theta being replaced with sine of minus theta. Remember that sine of minus theta, okay, is going to be just is minus sine of theta. Okay, so that's why that works. So keep that in mind. All right, so these are the symmetries. We're going to do some examples in the next video where we're going to actually graph some of this stuff. Obviously this can be done on your calculator, but let's see what we can do this without our calculator in the next video. So I'll see you then.